Okay, so today I'm going to walk you through your first heat run. This video will probably be 20 minutes long or something, but I'm going to try to go through all the inputs to heat and show you the things that you need to know for your first run. So under releases, if you remember, we went in and downloaded the app image and the test run. If we did that in another video. If we extract that tarball, the testrun.tar.gz, we have these 4 files in there. Today what we're concerned with is this PFC, which is a PFC from the lower diverter of NSTXU, the one highlighted in green here. It's called solid 843, and we're going to calculate the heat flux and temperature throughout this PFC, and then we're going to need this 842, solid 842 PFC, because it will cast magnetic shadows onto this 843 PFC. So both of them are included in this ibdh_2tiles.step, this CAD file, so that's what I have opened here. And so the naming that's in this step file is what we're going to be using for the rest of our input files, so it's important to note. So in order to run the heat user interface, once I've gotten the heat app image downloaded, I can just browse to the file that we saved the heat app image into. So here we have our app image, heat app image, and we're going to just run it. That's going to run and eventually create this Flask server that's running on a specific IP address, which it'll print. So Dash is running on 127.0.0.1 port 850, so we're going to browse there. And here we have it. This is the heat user interface. So at the top you'll notice this is the data directory. This is where data will be saved that we generate, and then the mount directory is where we've mounted the app image. The first thing, we're just going to basically work from top to bottom through this. So the first thing we're going to do is select our machine, that's NSTXU, and then we're going to come over into our tarball, and we're going to take this NSTXU test input and we're going to drag it in and drop it. So we drag and drop the input file, and then we have all of these populated fields. If we look at the input file, it basically has a bunch of variables and then the value. So like here's an example, shot, comma, 204.118. That directly corresponds to this box, shot number 204.118. So if you change something in this user interface, you would need to either update your input file, or you can save the settings directly into a new input file by using that button. Okay, so for the MHD, our first shot that we're going to run out of the test case is this 204.118, and then we're saying minimum time step of 0, maximum time step of 10 milliseconds. This is a very short period, but it's just for this example. And then we're going to take our G file, 204.118, and this is 4 milliseconds. That's the format here. This is a G file. To be explicit, it's a GEQDisc EFIT reconstruction that follows the format by Lau at D3D that was written up in 1997. So basically we're going to take this file and drag and drop it into the user interface. And so now it says it loaded it. We're going to make sure 2D Plasmas is selected because the 3D button will not work for this. And then we are going to run it or hit the load MHD button. That loads this graph over here, which is interactive. We can zoom in, we can zoom out, we can query the data. So there's a whole ribbon of stuff you can do here. So the last item in the MHD settings is this number of trace steps. And what that is, if I open Paraview, so here I have the STLs that correspond, that heat generated from a different run. So this isn't from this current run, but these are the same STLs that heat generated, and I have a field line trace here. So this is what happens when we run heat. We launch field lines from the surface of the PFC. Remember, this is PFC 843. This is one we're concerned with. We're launching field lines from the surface, and as we're walking up the midplane, every degree we walk, we're checking to see if we intersect with another PFC, and if we do, we say, oh, this is a magnetic shadow. So the number of degrees that we're tracing here is what we're defining. It's the length of this trace. So this one that I'm showing in green is like, I don't know, 50 or 60 degrees. I have a couple others here. So like this one is 360 degrees. You can see it's a full toroidal turn. So basically what you define in this box is how many steps up the magnetic field line do you want to check for magnetic shadows. And increasing this number will increase the accuracy, but also increase the computational time. So there is an incentive to keep this as low as possible while still maintaining a high enough fidelity. So we're just going to do 10 for the test case. Here in the CAD settings, I have the heat flux resolution in millimeters, 5 millimeters, and the intersect resolution in millimeters. That's 25 millimeters. We're going to change this to standard. So standard is generally a good bet unless you explicitly know what you're doing. So I suggest everyone use standard. Okay, so to describe these variables, let's go back to this image here, and I'm just going to show you. So remember, this is 843. This is the one we're curious about, the heat flux. So we have a box here, heat flux resolution, 5 millimeters. When we do that and we run heat, it's going to build an STL file. And it's going to build this file called solid843, and then it's going to name whatever we set the resolution to be. And if we look at the surface with edges here in ParaView, we can see the actual mesh. So this is a surface mesh generated by heat. And the maximum length of any triangle is 5 millimeters, is the variable that we set here. And so if we make it a smaller number, that means that every triangle will be smaller and we'll have a higher resolution heat flux, but it'll take longer to calculate the heat flux. And so let's look at the solid842 standard. So in the second box we have this standard, and what standard does is just makes a very general, it makes a high accuracy but with very few faces mesh. So if we look at that one with edges, we can see on these every castellation has 20, 30, 40 mesh elements. Here it just has 2. And that's convenient because as we trace up the field line, we don't care how many mesh elements are on a face. We actually want as few as possible to make the calculation faster. So you usually want your intersection resolution number to be bigger than your heat flux resolution number. Or if you write standard, that will find a very high accuracy but few face intersection face. So I suggest using the standard algorithm. So we're going to load those, and then we're going to take our step file, ibdh under two tiles.step. So there's a CAD file, and we're going to drag it in here. And it'll take a second, and then it's going to populate this. It says it loaded it. We can also see that it loaded it in the terminal. And then we're going to come down to PFC settings. So this file, ibdh under dash 2 tiles.csv, is called the PFC file. We're going to take this and we're going to drag it in here, and it populates this these columns. So we have time steps, which is 0 through 5,000. So what we're saying is this PFC 843, the one that we're concerned with the heat flux on, is the one under PFC name. We're going to calculate any heat flux from a magnetic equilibrium that we loaded between 0 and 5,000 time steps. Obviously this one's only at 4 milliseconds, and our bounds here are 0 to 10, but we're just saying anything up to 5,000 we'd calculate. And then we have this map direction variable, which is 1. It could also be a -1. And what that is I showed you this here. I'm going to turn off these surface with edges so that we don't have all that blue. So this is a trace in the direction of the map direction 1. And so basically map direction is a proxy for toroidal direction. So here's the 360-degree trace that I showed you before, and this is with a map direction of 1. If I change it to -1, it's going to go in the opposite toroidal direction. So this isn't useful for our heat flux calculation. This is -1. The white is -1 here. This is not useful because it's just going into the tile, and obviously power is not flowing from under the tile up. It's flowing from, as the yellow line is showing, from the scrape-off layer into the target. So the map direction is basically just a switch that's either forward or reverse toroidal direction. So you'll sometimes have to play with that to figure it out correctly. And then the diverter code, lower outer, corresponds to the power fractions that are defined down here in heat flux settings. So we're saying this PFC is in the lower outer diverter. So we want the diverter code LO. And so we can see we're going to use a P-SOL, power crossing separatrix of 10 megawatts for this run. And we're going to say 70% of that, so 7 megawatts, goes down to this lower outer diverter. And that's what the div code is for. And then intersect names are all the names of the PFCs that could be casting magnetic shadows onto this PFC. And if we look back here, this PFC could be casting magnetic shadows onto itself because there's little steps that are like, if I zoom in here, you can see these little steps, and those will cast magnetic shadows. These are in 843 in between the little castellation rows. There's also a bigger step here between 842 and 843. So both of those PFCs are included here in our intersect name. If we look at the file, the actual file, ibdh_utils.csv, it's the same data. There's a huge comment just to tell you how to write it. But if you're creating a new case, a new PFC run, you need to go in and create a new line for every PFC that you want to calculate the heat flux on. And you'd have to include all of the potential intersection PFCs, the map direction, which diverter it's in, and the time steps for that PFC. So this is just the generic PFC input file, and it can have as many lines as you want, corresponding to as many PFCs as you want. You just have to make sure the PFCs are in the CAD, obviously. So now that we drag and drop that file in, we're just going to load it, and it's going to build the meshes for that PFC. So what we see here, this is where we left off. So Heat figured out that mesh exists already, and so it didn't go and rebuild a mesh. So Heat will, once it creates a mesh, it'll check and see. Once Heat creates a mesh, it'll save it, and then the next time you run Heat, if it already exists and it saved it, it won't rebuild it because that is time consuming. So here it said, oh, the mesh already existed, so I'm just loading an existing one. And so we see it's solid 843, 5 millimeters, and solid 842 standard. So the 842 and 843, these were the values that were in our intersect names, and so those got the standard resolution, and then solid 843 had the 5 millimeters. That's the one in the PFC name, and so remember we had 5 in standard, so that's how this all fits together. So now that we've meshed all of our PFCs, we're going to come in here and select our heat flux settings. So there's 3 options currently. This will probably be expanded in future versions, but for now we have Gaussian spreading, which is Ike heat flux profile, basically exponential convoluted with the Gaussian. So there's also a Dan Brunner multi-exponential scaling, so that's a 4 exponential near and far scrape off layer lambda Qs in both the private and common flux regions. And then there's a limiter, which is a 2 exponential scaling with no private flux region. We're just going to choose Gaussian spreading from Thomas Ike's nuclear fusion paper. And if we look here, we can say Ike scaling. We can select Minkowski scaling. If you're choosing Minkowski, this is a scaling for the capital S, the Gaussian spreading parameter. It needs the Greenwald density fraction, and that cannot be calculated from the GEQDisc file, so you have to prescribe that manually here. It defaults to 0.6. And if we're choosing from Ike scaling and from Minkowski, these boxes will not be used. But if we chose user-defined, these will be used. So I could set this to be a user-defined lambda Q and a user-defined S. So for now, I'm just going to choose Ike scaling and Minkowski scaling. I'm going to leave the 10 megawatts of power crossing the separatrix. I'm going to leave it as a 30-70 split between the inner and outer diverter, and I'm just going to keep this off. Long-range intersection checking, you probably won't need that unless you're an advanced user. Let's just load that. Then we come down to the open foam settings. Open foam is the engine under the hood of Heat that runs thermal calculations. So this will solve for temperature throughout the PFC. We're just going to do a 10 millisecond run. This minimum and maximum mesh refinement levels are just the quality of our volume mesh, which OpenFOAM will create from our STLs. This is going to be a pretty low quality one, but it's fast and it captures about 90% of the time. This captures sufficient information. So I usually use this 1 to 2. If you wanted to increase this number to 3, 4, 5, that would create a better mesh, but it will also take much longer. This, on the first time you ever run this, it will maybe take a minute or 2 to create this volume mesh. And then the STL scaling and delta T, this is the scale factor if you had a different unit system. And then this is the delta t is the number of milliseconds, or sorry, number of seconds between time steps that OpenFOAM is going to run. We're not going to change any of that. We're just going to load it. We're going to come over to the heat run settings, and we're going to say, okay, give me a point cloud of heat flux and give me an OpenFOAM thermal analysis. There's all these other things that you can run. I'm not going to talk about those in this video. I'm just going to do these two. I'm also not going to talk about the traces. We're just going to run it. And so it starts, and it starts running, and what we can do is we can look over on our log file. This is expandable if you want. We can see what's happening. This is only updated every 5 seconds, so if you wanted more real-time information, we can look at the actual terminal window, and we see that we're just going through our steps. So we're stepping up the field line in degrees, so that was step 1, and we see 338 shadowed faces. Step 2, we see, we see 133 shadowed faces. So it's just walking up the field line and calculating shadows. And I'm going to let this run, pause the video for a sec, and then when it completes, I'll come back and finish it off. Okay, so this OpenFOAM run just completed, and we can see that here. We can also see in the GUI that the heat run completed. Yellow text has been illuminated. So this is a complete run. So we're going to go into pair view now. I'm going to turn off these field traces that I was showing you before, and we are going to open the heat flux data that just got spit out by heat. If you remember from the beginning, I said all the data will be saved here. So that's what we're going to browse to in pair view. So let's open a pair view window. And so that was home, Tom, heat data. And what we see is there are machine names in capital. So inside those machine names, we have STLs, the SDP files, and the 3D meshes that we use to generate all of the data. And then we have lowercase machine name _ shot number. So we're going to go to this NSTX _204118 because that's the shot we just ran. And we have 4 directories here. For the heat flux data, we're going to go into the time step with which we are concerned. That was 4 milliseconds. And I'm going to come into the pair view folder and open the heat flux all.vtk. If I apply that, we can see it shows up like this. And it might not look like this color. If you wanted to change the color mapping, you come over to this little heart folder thing, and you can choose. I chose black body radiation. I applied it, I closed it, and then you can use this little scale button, rescale to custom range, to change a range. Let's change this to 25 megawatts. And we can see that it shows up like this. We have all of our magnetic shadows that I was talking about. So here's the large band, which is because of this tile, 842, and then these small bands, which are because of the steps between each of these castellations. And we can see a large amount of heat loading right on this corner here. But keep in mind, we only ran this trace for 10 degrees in the GUI, remember. So number of trace steps, 10. So it's important that you keep that in mind when you're doing this heat calculation, because it could just be that it was farther up the field line where this is shadowed. So for this example, we're only going 10 degrees just because it's fast and easy and convenient, but you maybe will want to keep that in mind. One way that you can check that is with the power that comes out of the heat calculation. If we scroll back up here, we can see power to this diverter. So 7 megawatts was in the scrape-off layer going to the outer diverter, and this reconstructed 6.16 megawatts. And the reason this didn't construct, it should be within 2%. The reason this one didn't is because there's power on the next tile over here. But for the test case, we didn't want to include that. So if you included all the tiles that you're supposed to include, you should have a power that lines up with what was expected, the 7 megawatts. It should be within 2 to 5%. Anyways, that's the heat flux. We can see it here. If we wanted to like query the data, we can click on this hover points on, and we can just see, okay, this is a 34 megawatt load right here at the strike point. So yeah, it's all there and available. If we want to then see the temperature, actually before I open anything, I'm going to turn all these tiles off, and then I'm going to come back out to my shot So this is my data directory and then the machine under dash shot number, and I'm going to go to open foam. I'm going to go to heat foam. This is the tile that we calculated the temperature on, and I'm going to open solid843.foam. And what comes up over here on the left are all these different values. So we have thermal conductivity, we have the temperature gradients, we have this is thermal diffusivity, this is thermal conductivity. We don't really need all of that for this. We're just going to do temperature. So we're going to apply that, and that will open this mesh. Like I said, this is a coarse mesh because our min and max refinement levels were pretty close to each other. And then we're going to go to temperature. Oops. We're going to go to temperature here. And temperature will then give us the heat load. And we can see the same shadows appearing. Now remember that heat flux that we applied was at 4 milliseconds. So let's go to 4 milliseconds. And we can see the temperature here is capped at 5. So that's 5E2. That is 500 Kelvin. And we can see the same thing. Remember the heat flux we had on the edge here? We can see that coming out. We can see the strike point heat flux. And then we could go back here and just create a video from this. And we can see it just turns on and then decays off pretty quickly. Remember, this is only 10 milliseconds, so it's not going to be a very good thermal simulation. This is just an example. So it loads up the tile real quick and then it decays off exponentially. We can see that visually here. If we come over to the output tab of heat, we can see a lot of the values that like this is the Ike value that was calculated. This is the Mikowski S scaling that was calculated. If we come down here, we can see the time history of open foam variables. So the peak heat flux was pretty high, around 80 meg. And the peak temperature, we can see, goes up to 1200 degrees, 1256, just from that quick little flash of heat. And this could be because we had a pretty coarse mesh, so we'd probably want to run this finer heat flux, finer mesh just to be accurate. But we can see that at 4 milliseconds that heat flux is applied, the thing ramps up and then decays off in temperature, which is what we were seeing here in this little video. We have at 4 milliseconds a huge flash and then it decays off. I also have included a plot here, the QDiv distribution. So this is a log scale, but basically we can see how many points are super high, how many points are super low, and we can see the distribution of heat flux. If you ran a thermal probe, that would appear here. And then the last thing I'll show is if we wanted to download these heat results, we can hit this, and this might take a minute. If we look at the terminal, like I said, creating heat result zip. This may take a while for large open foam runs. So it just zipped the results because this wasn't too big, and then it downloads into a zip. So if we open that zip, we can see inside is the same, everything that was included in this directory under our time step is included in this directory. So that can be downloaded directly through the web browser. The other things that can be downloaded are the EQs, and you can download the input file, you can download a PFC file, so that'll all happen similarly. But that's the general overview of how to use heat. I hope the video was helpful. Yeah. I will probably include some other videos for specific use cases like field line tracing or something like that, but those should come a little later.